Okay, so the big picture goal for our students is that gradually over many years, and this is important, a student's mathematical education is slow and methodical. It does not come together like this. Gradually over many years, our students will develop into accurate and independent mathematicians appropriate to their respective vocations. Okay, so that could be, it may be the case that down the road, the only place they really use math is as a parent teaching their kids. That's fine. That's a vocation, right? That's part of our vocations as parents is to help our children with their schoolwork. That's fine. But math pops up, sort of in its own way in a lot of different areas. And so we want students to be able to independently be able to think about mathematics in their vocations. So what is mathematics? So the way I think about it is mathematics is actually particular habits of mind. All right, so it's a way of thinking, okay? Habits of mind that seek to describe and discover quantitative structure and order. Okay, so this is important. It's about trying to make sense quantitatively of things, trying to see structure that kind of fits things together. And so if you think about it that way, it's not just about equations. It's not just about finding the right answer. It's about trying to understand the structure and the order of of quantitative things that God has made. Okay, both for its own sake and for application in God's creation. So this is important. That mathematics is a discipline in its own sake, trying to understand kind of structure within mathematics, but then that is actually applicable to things outside of mathematics. But if we kind of just get stuck on, okay, it's only the applications that matter, we sometimes start to miss the beauty of the structure and order within mathematics itself, okay? So both are important. We don't want to be sort of like so stuck in the beauty and order of mathematics that we can't apply it, but we also don't want to be so focused on applications that we miss the intrinsic beauty in math. So how do we nurture these habits of mind? So this is where our classical approach to teaching at Trinity is helpful. The first way we nurture these habits of mind, and this is what everybody's familiar with, is in math, is mimetic teaching, right? Mimetic is to mimic, okay? So the teacher demonstrates something on the board, and then the students then replicate that. Okay, it might be, multiplying two-digit numbers, right? So the teacher demonstrates that, and then the students are asked to replicate this. All right, and it becomes more complex as you get higher in mathematics. This is absolutely important. All right, it's absolutely necessary because mathematics it's a technical discipline. There's skills that are involved. Students aren't just going to discover these things on their own. They actually need to be shown. So this is absolutely necessary. But it's usually insufficient by itself to actually develop mathematical habits of mind. And that's for a number of reasons. First of all, students will inevitably run into problems that don't exactly fit the way the teacher did it on the board. This happens in every textbook. No textbook can go through all the possible examples that students might see in the exercises, all right? So students are inevitably going to get into problems where, well, this isn't exactly the way the teacher showed me, okay? So what do they do then? What do they do then? If they only think mimetically like this, they're stuck. Students may accurately mimic the steps that the teacher is doing, but they don't really understand them. They don't understand where these steps are coming from. They don't understand why they work. And that then becomes a problem if you want to translate it to something that's a little bit different because they haven't actually thought deeply about it. And then the other thing is if it's just, the teacher looking at the output of the student's work and it's just mimetic teaching, the teacher is just assessing on the answer. Okay, and the thought processes that went in can sometimes be hidden and unknown. Okay, so that the teacher actually doesn't really know how the student is thinking about the mathematics. They just see whether they got the right answer or not. All right, so that's why mimetic teaching it's absolutely necessary but insufficient. So the way we try to actually get to a place where we can not just be relying on mimetic teaching, but have a deeper understanding is by asking questions. Okay, just asking questions during the class time, and as you as co-teachers at home. So Mrs. Spangler actually briefly mentioned this in her presentation. She was saying, well, your logic rhetoric student comes to you, and they have a problem, a math problem that they don't know how to do. Neither do you. You don't know how to do it either. So what do? What do you start doing? You start asking questions. That's the key. Questions are absolutely necessary. And in a classical setting, this is akin to what's called Socratic discussion, where by using questions, you actually try to dig deeper and deeper into actually what's going on and how you're thinking about things. So the long-term goal of this is that the students can ask questions internally within their own heads. And they don't need to be reliant upon you to be asking the questions. They're actually doing their own questioning. And this is what's called metacognition, where students can actually reflect upon their own thinking. And this is difficult. It's difficult for all of us to do. But ultimately, that's where you need to be able to get, is to be able to have metacognition where you're reflecting on your own thinking and evaluating, asking yourself questions. And important is that these questions themselves are the habits of mind of mathematics. It's really, math really isn't that mysterious. It's actually pretty much just about asking questions and trying to, get your head around those questions and find a way to navigate through them and find some solution. So doing this in the context of rich, interesting problems is particularly fertile ground for developing these habits of mind. Now, this is a challenge for all of us as teachers in the classroom and as co-teachers because, we want to get through a lot of material, and that material has a lot of little pieces. And so you want to have sort of exercises that sort of focus on those pieces. But sometimes it's nice to actually have problems that aren't, sort of focusing on one piece, but actually have a lot of things going on, and that can become really fertile ground for discussion. So these questions can foster understanding, accuracy, interest, and metacognition. So examples of questions to ask. What exactly is confusing me about this problem? All right. Our students are very easy, they very easily say, I don't understand what's going on, right? Or I don't understand this. Well, what exactly is confusing you about it? What do I know for sure in this problem, right? You want to figure out, okay, what do I actually know for sure? I need to find this. I don't know this, but what do I know for sure? What do I need to figure out before I get to that final solution? Okay, so this is where I want to get at, but there's probably some things in between that I don't know, and I need to identify those things that I need to figure out. Have I seen a problem like this before? That's where the mimetic teaching is going to be helpful, because the teacher has already shown them quite a few problems. But what makes this problem different from others I have just done? What makes it similar? Because that problem might not be exactly the same, and to be able to identify what's different versus what's similar can be helpful. Can I look at this in a different, more illuminating way? So often we approach a problem and we see some things going on and we kind of lock in on that. and then we just don't get anywhere. What you need to do is to be able to step back and say, okay, can I leave off what I've locked into, and maybe there's a different way to look at things. What makes this problem interesting? All right, that can be helpful for students because it will actually engage them in the problem. Are my calculations accurate? Can I explain them? Right, so we're used to thinking about that. Have I made any classic errors? Right, so as you go through your students, for example, in early grades in grammar school, classic errors are just to kind of like mix up operations. I'm supposed to be adding two numbers, but I multiply them, right? Classic errors. And then even if they've gotten the problem correct, I like to ask my kids, well, how did you think about it? Because I want to know, okay, how did you actually get there? How did you think about it? And that gives them an opportunity to work on, connecting mathematics with language, which is really important. Students tend to think that math is sort of its own little world and has nothing to do with speaking or writing or anything like this. No, they connect, all right? Why does this work? Do I understand the logic of this problem? Am I fuzzy about anything in this problem? That's important. If you come to the end of a problem and you're fuzzy about something, that meaning that you just, okay, like if somebody asked you about it, you'd be like, I'm not sure. You kind of have to start to realize when that's happening, because that means there's something that you don't understand. And that can be an opportunity to kind of be able to talk about mathematics and understand it more deeply. Okay. So that's sort of what the kind of the outline of things that I wanted to discuss. Any questions about these? Okay, let's now do this together. Okay, so I'm going to give you a problem here, and you should all kind of view each other as each other's co-teachers and see if you can ask each other questions to make your way through this problem. You can do this problem, Steve.
What number are we?
Maybe.
I would start to see whether or not these are the same shape.
Hey, listen. Extra square. This one?
So a first clarifying question would be, what's the extra square I'm talking about? Does everybody see the extra square that I'm talking about?
I mean, I assume it is this.
Yes, it's that empty square sort of right down there at the bottom. Yeah. So in moving from picture A to picture B, this empty square has appeared. And why is that weird?
It appears as if it's not part of the shape, or that the shape is no longer a triangle, it's something else.
Yeah. It seems that
This might be a copying issue.
Oh, you mean like the photocopy?
Right.
No,
Your
it's not a
copy
photocopy issue.
transfer.
It's not a photocopy issue.
So the problem is that all of the shapes appear to be the same between the two triangles, and we have simply rearranged them. So all of a sudden, magically, one is bigger than the other.
Yes.
Where did that space come from? Where did it go?
Yeah. So here's a good question. What do you know for sure in this problem? What do you know for sure in this problem? And going from A to B, what do you know for sure?
The boundaries of both triangles are the same, meaning like the 3 points are in the same, they are similar, they are the same.
Right.
It looks like Tetris.
It looks like Tetris. Yeah, it does look like Tetris. Yeah. So I heard somebody mention we should check to make sure that those shapes are the same. So do you see up top there's a dotted triangle, right? Triangle with dots in it. Is it actually the same as that triangle with the dots on the bottom?
Yes. Yeah.
Yes, it is, right? It's a right triangle. It has a leg of length 4 on the left, and then it has a base of length, what is it? 10 on the bottom. Yeah. So those dotted triangles are the same. They're congruent.
The dot and the big triangle stripe have been reversed
Yes.
from the top to the bottom.
Yes.
We know that.
Do you think the other shapes have been preserved? Like say the large the diagonally dashed triangle. Is it the same on the top as on the bottom? You think so, Sarah? Yes, I think so too. Right. It has a left leg of length 6 and a a bottom leg of length, I think it's 16. And then those funny shapes, I guess they're technically weird hexagons, right? They have 6 sides, but they're more like Tetris pieces. Yeah. Are they the same? Yeah.
Yeah,
Yeah.
they are.
It
Seems like all the shapes are congruent, but I feel like that's got to be wrong. I feel like I'm counting something wrong. Well, you're counting everything right. Yeah, how is this fit?
So what's the problem in our minds with this? Why does this not seem to be like it should be true?
Because if they're the same size, the area should be the same, but there's
Yes.
a piece of missing area at the bottom.
Yes. If all of these individual pieces are congruent, then the sum of the areas on the top should be the sum of the areas on the bottom. But it doesn't seem like that's the case because there's this extra area on the bottom that doesn't appear on the top. Yeah.
So if I'm not mistaken, and I'm just as likely am mistaken not, when I do the area of these 2 rectangles,
Yeah.
and rectangles, on the top one you end up with 60 for area. On the bottom you end up with 64, which is 4 different than the bottom ones. So,
Well, right. So on the top, those funny Tetris pieces, you're saying, okay,
Right.
they add up to an area of 60.
yes.
On the bottom, those funny Tetris pieces, they have an area of 60, but then there's this extra area of 4.
I'm going ahead and just count.
Yeah, there's an extra area of 4 that's missing.
Aren't they just arranged in a different order?
They have been arranged in a different order. Yes. Okay, so we talked about these 4 individual pieces, right? Is there another shape in the top picture that we can talk about?
You can think of the shapes individually, but you can also think of the shapes as a whole.
As a whole, yeah. So what is that shape as a whole that's formed on the top?
A rectangle.
You mean the 2 Tetris pieces together?
All 4 together. All 4 together.
Triangle.
And on the bottom,
Convex polygon? Concave polygon?
oh, right, because of this little indentation. Yeah. Okay. All right. So if we included that little indentation in our figure, right? So we've got this figure on the bottom. Let's get sketch it here. All right. If I include these empty squares in this figure, how would we describe that figure?
Triangle.
Okay. All right. So if this is a triangle on the bottom, and this is a triangle on the top, what's the problem?
Is an area?
They should have the same area, right? Because as Mr. Williamson pointed out, they have this, the distance between this vertex and this vertex is what? 10, right? And the distance between this vertex and this vertex is 26. And it's a right triangle. So that means this right triangle on the bottom has to have the same area as the right triangle on the top. But does it?
No.
No, it doesn't. So something's wrong. So here's where we have to look at my little question here. Can I look at this in a different way than I have been looking at it? Because I'm locked into, this is what I was talking about. I've kind of locked into a way of thinking about it. And it doesn't seem to make sense. The area of this big figure on the top is supposed to be the area of this big figure on the bottom. But it's not. So there must be something I'm missing. Can I think about this in a different way that starts to explain what's going on?
Well, if I were at home, we'd just crumple it up and throw it away.
So yeah. Well, we want to be more determined. I was talking to Kelly about being determined. This is about being determined.
Could we recalculate the area of each of the pieces?
I mean,
And I'm counting them and they're the same.
yes,
right?
yeah. You know for sure. So this is an example. What do we know for sure? We know for sure that those individual pieces are the same. The dotted triangle is the same as the dotted triangle on the bottom.
I mean,
The dash triangle is the same.
How they're in there.
Yeah. So we know for sure that those individual pieces are the same.
But how does the configuration change?
Yeah. There's something that we've locked into in our thinking that we have to unlock ourselves from. We got to figure out what it is.
Do we not want to think about it as far as area?
I know. It's
I mean, they don't have to have the same area, do they?
Well, they don't.
Why don't they have to have the same? Obviously, they don't have the same area, right?
Right.
Big figure on top does not have the same as the
area.
big figure on the bottom. They don't have the same area. So there must be something we've kind of assumed in our heads that's true, that's not true. And this is where we have to we have to figure it out.
This is where I don't do well. Where did the extra square come from? Wife got mad and rearranged the living room.
So one thing that is on the list is, can I draw a picture or diagram to help me solve this problem? So if I cut all of the pieces out individually and laid them on top of one another, would that
That
help open my eyes to?
it could. That's true. I didn't bring scissors, but that could.
Well, it's not
The two
square.
two triangles. If you flip this one, hold on.
Right, it does come out to 260 square units if you turn each into a rectangle. Well, minus those 4. I was trying to do that thinking as well.
And you could put it right here, but if you were to actually flip it into place, it's different. Right?
I don't think so,
Only scissors.
because you got 10 up and 60 over.
Okay.
In both cases, you just have that 4 minus that 4.
But I'm saying just the dotted triangle.
Oh,
You
okay,
could
I'm
cut
sorry.
it out and put it right there, but if you actually had to flip it and put it there, it would not work. This piece could be moved here. This piece could be moved here. This triangle could be transposed on top of that one, but the dotted triangle could not be.
Well, the dotted triangle, we wouldn't flip it. We would just kind of translate it and put
But
it
they
on top.
can't all be that way. One piece is going to have to be, right? Oh, I guess not, because then this one could go
They-
directly
yeah,
there. Okay. Okay.
I here. I'll give you a hint. Okay, I'm gonna focus on the top piece. Okay, and I'm gonna write out the lengths of the sides of these triangles. All right. So this isn't drawn to scale. This is 4. All right. This is 10. All right. This is 6, and this is 16. Okay. And so I want you to focus on this triangle and this triangle. And you notice something about the numbers in this little triangle versus the numbers in that little triangle.
The width still adds up to 26, but then transposing my head. The height's still 10.
So this goes in, and this is where
Area is 1.3. Or 1.3.
where if I have a triangle here, okay, and I make a straight line here, okay, and I make a straight line here. This goes into stuff that we've thought about it sometime in our lives about geometry. This line is parallel to this line, right? All right. This line is parallel to this line. Okay. Okay. So I've got a parallel line here, and what do I know about this angle and this angle?
They're congruent.
They're congruent, right? These are what are called corresponding angles, right? I have this line cutting through these parallel lines. These two things are congruent, okay? Now, I've got this parallel to this. So what do I know? So these lines are parallel, and I've got a line cutting through here. What do I know about this angle and this angle?
Congruent.
They're congruent too,
Yeah.
okay? They're congruent too, all right? So do we have some, and this is a right triangle here. They're both right triangles. Do we have some, so this little triangle is not the same size as that triangle, but we have some language back in our mathematical education that says these two triangles satisfy a relationship. They're what are called similar triangles. Similar. This triangle is has the same angles as this triangle, so I could kind of just blow this triangle up and it would get to that triangle. Okay, so these are two similar triangles. Okay, so think about that, and now think about what's going on here.
The big triangle we're working with overall is similar to the smaller triangles.
It should be, right? Yeah. So this big triangle here is similar to these smaller triangles, all right? Here's another little fact about similar triangles. If I have say this is 2 and this is 3 and this is 4, what's going to be the length of that side?
6.
6, right? The legs on similar, or the sides of similar triangles have a similar ratio. 2/3 should be the same as 4/6. Do we have that here?
No, right?
No, we don't. What's the ratio up here?
I mean, the legs.
2/5, right? 4/10.
Yeah.
4 over 10, 2/5. So the ratio here for the legs is, let's just put it in here, 2/5. And what's the ratio here? 3/8. So the conclusion then, what's the conclusion then?
The triangles aren't the same.
They should be similar, but they're not.
There's even a more fundamental conclusion. It's not that the triangles aren't the same.
They're not triangles?
They're not triangles. They're not triangles. So we locked into this idea that this big thing was a triangle. All right? We locked into this idea that on the top, this big thing was a triangle. And we locked into the idea that this big thing is not that this big thing on the bottom is a triangle. But they're actually not triangles.
Is this a
Okay? So because they're not triangles, they don't have to be congruent.
Oh my gosh.
Okay, so this figure right here. See, if you go back and you watch the video, I was very careful to always say this figure. I call it this figure on top. This figure here is not a triangle. Okay, it has it's actually a quadrilateral. If I drew it in an exaggerated way, this would be a straight line. This would be a straight line. All right, but this thing would kind of come down like this, and that thing would go like that. So it's got this concave, and it's a concave quadrilateral.
Oh.
All right? And then when you go to the bottom, what's happened is the bottom's a quadrilateral too. All right? It has the same length as this side, same length as this side, but now it's a convex quadrilateral. It comes up like this and like this. So there's been extra area added that has to be taken away down there.
Which is why it doesn't go perfectly through the center.
It doesn't go. Yeah. If you look at your picture.
I never put that together.
Yeah.
When I was drawing the line, when I was following like the lines this way, I noticed that the squares didn't always line up like.
Yeah.
And you weren't getting halves on your little graphing.
No, yeah. If you look at it carefully, this what we thought was a line up at the top, the hypotenuse of our triangle, it's actually not a line, and it's not passing through the same points. Yeah. But your eye can't see that immediately. Okay?
If you hold, I guess there's a slight, if my paper is completely square, I guess there's a it's such a minute.
Yeah, it's
ooh, yeah. You can't see. Yeah.
It's so subtle. I would convince myself the line was just a little long.
You have,
yeah.
You have to hold the paper up and sight down the line. It's the only way they.
Yeah.
Very subtle.
Yeah. So you really can't see it by eye. But the point is the mathematics told us what was going on. The mathematics told us, I have a triangle here. I have a triangle here. They are not similar triangles. Therefore, the whole big thing cannot be a triangle. Because if it were a triangle, these would be similar, but they're not similar. Hence, this can't be a triangle. So you figure out that it's actually a quadrilateral. Okay? So
if we had cut them out and placed them on top of each other, assuming that our scissor line was perfect.
yeah. You might have been able to see. Yeah.
Although I would have just assumed that I cut crooked.
Yeah, me too.
Right. You might have been able to see it.
It's just a little.
You can put a straight line across it and you can see it.
It's weird that little sliver, though, adds up to 4 units.
And yeah, that's impressive.
Right. You know?
This difference that you can barely see actually adds up to 4 units. That's actually pretty impressive. Yeah.
Yeah, that's true.
So there you go. That's an example of sort of a rich problem that is confusing, that you just kind of you got to ask a lot of questions of, You had to get a little help from the teacher. But yeah. But the point is at the end, then you can actually see what's going on, and hopefully you have a better understanding of when you first looked at this. Okay. So I have another example problem here. It's a little bit more straightforward. But it might kind of push us a little bit because so we've been talking about right triangles here. This involves a little bit of right triangle trig. Am I running out of time? I still go for a while, don't I?
11:05.
Yeah. All right.
I'm going to need an extra copy of that because this would be a good evening argument at home.
We're so smart. Right.
No. I saw this on YouTube. So.
It's so cool. It is so cool.
Yeah, and you're a math person, so
I would have never done that.
So this is not so such a mystifying problem, but it's still kind of got enough going on. All right, so in traveling across a coastal state at sea level, so we're at sea level, not really rising in elevation. We're going inland, and we see a mountain in front of us. All right. Its angle of elevation to the peak from sea level is 3.5 degrees. So if you have a little sextant or something like this, you measure an angle of elevation of 3.5 degrees. But after you drive 13 miles closer to the mountain, the angle of elevation is 9 degrees. Approximate the height of the mountain. Okay.
Are we assuming that we're measuring from the ground level, or do we have to factor in our height?
No. You assume that you're at ground level at sea level.
Okay.
Yeah, just for simplicity. Okay. So here's an example where, if your student comes to you and you say, I don't understand this. And you're in the situation that Mrs. Spangler described this morning where you don't understand it either. You kind of start asking the student, okay, well, what have you been talking about in class? That's what I ask my kids. What have you been talking about in class? So that's the first question. And they say, well, we've been talking about right triangle trig. So we've got a right triangle here. Okay, and there's an angle here. What do you guys remember about right triangle trig? If this is my angle, I have 3 sides. How would I name those sides with reference to this angle?
Like the sine, cosine, hypotenuse, like that's
Yeah.
the long one's the hypotenuse.
Yeah.
I always got confused about sine and cosine.
This would be the opposite side, right? And this would be the adjacent side, right?
Okay.
And yeah, there's these. So for my little angle here, the sine of this angle, it's going to be a ratio of 2 of these sides. And I always remember the little mnemonic so, ka, toa.
Me too.
Yeah. So sine of the angle is going to be the opposite over the hypotenuse. And the cosine of the angle is going to be the adjacent over the hypotenuse. And the tangent of the angle is going to be the opposite over the adjacent. So you talk to your student and they know that much, all right? They can tell you that much. Okay, so with that in mind then, why don't you look at this problem and start to think about what kind of questions you could ask your student about this problem, because they're still stuck. What might be some good kind of probing questions to ask them?
So I'm just spitballing here because this is above my level of math. But
Yeah.
can you create other triangles out of these shapes? Like how many different triangles can you create? Are there similar triangles here that are hidden?
Yeah, where are the triangles? Yeah, we got to find the triangle. What triangles are we talking about? So I got this little picture here, right? What are the relevant triangles?
So like I started drawing right angles at different points. Like at the 13-mile point, you can draw a right angle up and you can figure a triangle, a smaller triangle there that has a relationship to the big triangle overall.
Okay, so you could you could drop a perpendicular here and make a little right triangle there. You're saying?
And there's
Yep.
some relationship between that and the big triangle, which has the measurement of the height that we're looking for.
Right. There's another triangle that we can draw in. That's a right triangle
Straight from
that
the
we
peak.
care about. Yeah, right. We drop the perpendicular from this peak. All right. So we've kind of got all right. So we've got a big right triangle here. We've got a little triangle, right triangle there. Do you see any other right triangles?
No, but now you can figure out this angle
The 9-degree one also makes a
because you
right
have
triangle.
9 degrees here.
Right.
It would be 180 total. So you could find out the angle
That's true.
missing.
That's true. Yes, I have another right triangle right here. This is 9 degrees. This is 3.5 degrees. So if I wanted to, I could find these other angles up here. Yep.
Yeah,
Yep.
you wanted 5.5.
Yeah. So this would be 81 up here. And then the big one
Be 5.5, right?
would be 80.
Oh, the big one. Oh, so that'd be 81 plus 5.5, so that'd be 86.5.
86.5, that sounds right. Yep. Okay, so we're starting to see that there are things that we know, right? And I know that this distance is 13. Okay, so I know some angles. I see some right triangles. I know that's 13. And your student says, well, here's another good question to ask your student. All right, what's actually confusing about this problem? All right. And your student might say, well, look, if I knew, say, like that this was 9 degrees, and I knew that this was 13, and I needed to find that height, the student would say, I could do it. Why could the student do that? Why could the student find that height?
Because they can use tangents.
They can use tangent, yeah. So remember, each of these things, we know what this angle is, right? It's 9 degrees, okay? And so tangent of 9 degrees is something I can evaluate on my calculator. It's some number. It's just a number. This is some number, tangent of 9 degrees. The opposite would be my h that I want to find, and the adjacent would be my 13, and I only have one unknown, and I can solve that equation, right? Multiply both sides by 13, and I can solve for h. So your student's like, I know how to do that. And so then you ask them, well, what specifically then is getting you confused? And they say, well, in this problem, I don't have this, because, like, okay, they say, okay, I got this big triangle here, right? And I'd like to find h, and I know it's angled, but I don't know the whole length of this side. I only know that this piece is 13. And then they say, well, okay, but then I've got this triangle here
But we have one piece that we've already figured out.
that I know it has an angle of 9 degrees, but I don't know what this is. Yeah.
Which is a fun little factor.
Well, if we have the height on that side and the two triangles, do they need to be congruent? Can we then find the other?
The red triangle and the purple triangle are not going to be congruent, but they both have the height as one of the sides. All right. And so if I knew this length, I could find h using the tangent, but I don't know that length. And that's where your student's confused. So,
But if I knew h, I could find x. We'll call it.
let's call this length x. If you knew h, you could find x. That's true.
And so, like in my head, like, is there a way that you can find the small dotted line there? I don't know, call it a or whatever. And then use a proportion to find h, because you have the 3.5, and then you have like a proportion between that, and you can find h, and then you can go back and you could find the proportion between 13 plus x to find x using a proportion between the two triangles. I'm explaining this badly, but
No. You're saying I could find this height. I would know what this is.
I can find the height.
And then this little triangle here is similar to the big one.
And so I should.
And so this over 13 would be equal to h over 13 plus x.
Okay, because the one.
Okay, so I would have a number.
9 degrees plus this is 13 miles.
I would have a number equaling h over 13 plus x. What's bothersome about that equation for us?
We have two variables.
We have two variables. Yeah, I can't solve two variables with one equation. How do I solve for two variables?
You need two equations.
I need two equations. All right. So can we come up with two equations?
The number equals h over 13 and the number equals h over x.
Can we back up for a hot second? On this triangle that you drew with the 9 degrees, how do we know that the bottom is 13?
No, we don't.
Okay.
No, yeah, this is not. I'm saying that our student would say if I had that, I would love it.
Okay, I'm sorry.
But you
I'm so
don't.
hung up on that.
I'm sorry. Yeah.
Move
Good. Yeah, we need two equations. Okay. And there's various ways you could find two equations, but let's just go with my basic red triangle and my purple triangle. Can I write down two equations, one for my red triangle, one for my purple triangle?
Well, we know all three angles of the red triangle.
Yes.
So could we find the length of the total bottom if we could solve for h?
I have a question. Oh, sorry, you guys.
Well,
Yeah, no.
remember, we're trying to use
smarter
these
than I am.
right triangle trig functions, okay? And we saw that if I have an angle, the tangent of that angle is the opposite over the hypotenuse. So could I just, what would that look like for the red triangle?
3.5.
Tangent 3.5, which again is some number that we can find in our calculator.
Equals h over 13 minus x.
13.
I mean,
13 plus x, yes, 13 plus x, yes. 13 plus x is the big red side, yeah. And then for the purple triangle, what would we have?
9 equals
Tangent 9 degrees
h over x.
equals h over x. Okay, so now we're a bit happier, right? Because we've got two equations, two variables. Okay, well now we got to remember how to deal with this. But your student, once they get to this level, they'll be more comfortable with this because they can see, I can take this, I can multiply both sides times 13 plus x. So I get 13 plus x times tangent 3.5 equals h. Right?
Oh, so you can plug that in for h on the second equation.
Yeah. And so over here, you can have h equals x tangent 9 degrees. So I have two expressions for h.
what's the algebraic term? Wait, is it substitution?
Yeah, I'm doing substitution. Yeah. So yeah, I could have taken this thing and substituted it in for here. I'm just kind of doing it another way. I'm solving them both for h. And then I can set them equal to each other, right? So I can set them equal to each other, right? So I have 13 plus x times tangent of 3.5 degrees is equal to x times tangent of 9 degrees. And now I'm going to be able to solve this for x, all right? This is just going to be a number times x. This is just going to be a number times x. I can handle that, all right, once I know what those numbers are. And then once I found x, then I'm happy because then I know this side, right? And I can just, well, I could say just plug it right in here. H is going to be equal to x times tangent 9 degrees, and I'm going to be able to find h. Yeah. So this is an example of a problem that is what I said, it's more difficult than the ones that the teacher probably showed them in class. The teacher showed them problems like this in class. But now this is a problem where they actually have to synthesize a few different things. They have to keep on using their right triangles and their right triangle trig, but now they also have to have two equations and two unknowns, and they have to figure out that they need to do that. So
Geometry, trigonometry, and algebra all.
yeah.
They're having
So asking questions as you go through it, actually brings them along, all right? Brings them along, brings you along too. Well, you might both get stumped, but then they still know what the questions are to ask when they come into class next day. They have much more informed questions. It's not just, I didn't understand this. It's, I know why I'm having trouble with this. I tried this and it didn't work. Can you help me sort it out? All right. So yeah. So the goal is to not just rely on mimetic teaching, where the teacher does the problem, students replicate it, because that has limitations. It only allows you to go so far. You actually have to get into deeper understanding and more difficult problems. You need to be able to use Socratic discussion, asking questions, and figuring it out together, so that hopefully your student actually internalizes this, and they can start asking themselves those questions as they approach their math problems.
May I ask, what classes are you teaching this year? I'm
teaching pre-calc and trig. Yeah, I mean it's one class. Yeah, it's just pre-calc. Yeah. So that's what I wanted to go through. Hopefully, it's been helpful, not too painful, and you can try to implement some of this in your co-teaching. Any questions before we adjourn?
Who's teaching pre-algebra? Are you teaching pre-algebra?
No, Mr. Garcia, pre-algebra.
And technically, 8 is the pre-algebra.
Yeah.
Yes.
We have 2 pre-algebra, so.
Okay.
Okay.
Okay. All right.
About the